Hello everyone and welcome back. Today we are going to discuss about true position. So let's get right to it. First, let's start with generalities about the true position. Let's see the symbol. So here we have the symbol of the true position. You can identify the symbol on the drawing very easily if you think about it like a mark. Basically, this is what it is. It's a precise mark on a measured part. Then we need to define the true position, and it goes like this. A zone within which the center point axis or center plane of a feature of size is permitted to vary from a theoretical exact dimension in relation to a reference datum. We can also see here the criteria that it needs to meet in order to be considered a true position. So the tolerance type is a location. Features that can be evaluated as a true position are points, including circles, spheres, intersections, planes, or lines. Datums can be plane, line, point, preferably in this order: primary, secondary, and tertiary. A few words also about the tolerance of the true position. So the tolerance of the true position represents the maximum admitted value doubled from the nominal position. We have to understand about this affirmation that the true position doubles the value of the deviation. So as an example, we can see here that we have a nominal of 20 millimeters. The actual deviation from the nominal on a measured part is 0.125. So let's say that this is on a z-axis, right? And the true position value will be 0.25, so it will double the actual deviation on the axis. And let's see now who is the founder of the true position. So Stanley Parker developed the concept of true position. In 1940, Parker published notes on design and inspection of mass product engineering work, the earliest work on geometric dimensioning and tolerancing. In 1956, Parker published Drawings and Dimensions, which became the basic reference in the field. Even the credits for GD&T origins is given to Stanley Parker. So thank you, Stanley Parker, for the work you have done in order for us to understand better what the world of GD&T is and to work in this field. Now let's see the types of the true position, and we can see that we have three types of true position: rectangular true position, diametral true position, and spherical true positions. So first, let's check out the rectangular true position. The rectangular true position is represented by a point, a symmetry point, a line, an intersection, or a projection point. It is constrained by one or two theoretical exact dimensions and by datums. This means that the evaluated feature has to fit between a rectangle equal to the tolerance. In this example from below, we have a connector type part and a requirement of true position of the pins in accordance to datum A and B. So here is the requirement, here are the datums, right? And in the right corner I set an actual deviation and what it can look like in a rectangular true position. So here is the point, here is the rectangular true position of 0.2 according to the tolerance, and here is the deviated point in that tolerance true position. Okay, now let's see the diametral true position. So the diametral true position is represented by the symbol of the diameter situated in the tolerance frame in front of the tolerance. This means that the evaluated point has to fit inside the diameter equal to the tolerance from the frame. And here we have the example, a rectangle type part with a hole in it that has to be at 10 mm from datum A and at 0 mm from datum B. And that's how you will evaluate the true position of 0.2. We have here the tolerance zone, but now it's a diameter according to the diameter from the tolerance frame, and the point deviated from its center that represents the actual value measured on the CMM or on other devices. Good. For the spherical true position, we have to know that the spherical true position is represented by the symbol S right here, situated in the tolerance frame in front of the tolerance and the diametral symbol. This means that the evaluated point has to fit inside the sphere equal to the tolerance from the frame. This is the only case where all translations are relevant in order to evaluate the true positions. So, exactly like in the previous example with the circle with the hole inside the rectangular type part, here we have a sphere and it's exactly the same. It has to fit at 10 mm from datum A, at 0 mm from datum B, but it also has to have the center at 5 mm from datum C. So all three translations are relevant for the true position in this example. Good, now let's see some examples. First, let's check out the evaluation of the point in the true position, because we do have a lot of geometries related to the point. As we can see here, we have the pore patterns, the circles with the maximum material condition, the least material condition, and the spheres. So we can find on the drawing true position related to points like this. True position of a circle will be represented like this. True position of a sphere will be represented like this, but you already saw that in the examples before. A bore pattern will be exactly like this, but it will also have the times and how many holes do you have on the part with the exact diameter, right? So if it will have I don't know, a diameter of 10, and then it will have a diameter of 11 and 12 and so on, then it will not be a bore pattern. All the elements, all the bores from the part, it has to be the same diameter in order to respect the bore pattern. Then the true position with maximum material condition will be like this, exactly like this, and with the least material condition we'll have this symbol. So this will be the symbols for the maximum material condition and the least material condition. And here it's an example of a hole, right? So the center point and where it should be, this is the actual form of the hole, right? Exaggerated, but it's the actual form. And this is the theoretical dimension D1 and the theoretical dimension D2 at the center, and here is the real position measured on the part. Then we have the position of the plane. So the extracted plane has to be between two planes with a distance between them of 0.5 millimeters according to the tolerance from here. The plane has to be at the theoretical exact dimensions of 50 millimeters from datum A. Okay, so remember that it will take in consideration also the rotations of the plane and the datum. So in order for the plane to be at a theoretical exact dimension from datum A, it has to be parallel to it, and all of its points, all of its extracted points, to be at a theoretical exact dimension of 50 millimeters from plane A, from datum A. And for our last example, the line. The extracted median line in this example has to be included in a cylindrical zone because of the diameter, because of the symbol of the diameter. This is why we have a cylindrical zone with a diameter of 0.5 millimeters. Its axis has to be at a theoretical exact dimension of 125 millimeters from datums A and B. Okay, so this is a rare case. Usually a hole, if its length is high, we will see true position on different sections of the hole. So you will see probably from this surface from here a section right here at, I don't know, 2 millimeters to see exactly what is the true position at 2 millimeters, because it will have a value, as we can see right here, at the center where it will have another value. Most likely it will be like in this example, closer to the nominal value, and another section at, I don't know, let's say that the part is 50 millimeters, then we will see at 45 millimeters a section right here, and we have to evaluate the true position, and the value will be in the other direction. So at the top it will be at plus direction, at the bottom it will be at minus direction from the center. So if you managed to make it until now, I will appreciate it if you can leave a like and share this content. Let's see the special content for the true position. Also, you can find this presentation and the Excel formula in my Patreon channel for free. So do go there and check that out if you want. And if we talked about the Excel calculator, let's see what this is about. So if you want to calculate the true position formula in Excel, you will have to insert the nominal values on the axis. Let's assume that you have two axes. The actual values on the axis, the deviations from them, so you can subtract the nominal value and the actual value from the x-axis, for example. Do the same for y direction, y-axis, and then use this formula from here in order to evaluate the true position. Okay, now let's see the special app. And also you can have a true position calculator from elogic.com. I will leave a link in the description below for this, and you will have to go to this website and download the true position. After this, you will have this true position formula. Double click it, and you will get this calculator. You can also add the maximum material condition right here, but you will have to have the diameter, of course. So let's say that, I don't know, we have a maximum of 10.1, a minimum of 9.9. Actual hole diameter is 9.987. The maximum value on wide is 21, the minimum is 20, and this is the nominal value. The actual is 20.357. For X dimension is, so notice that it already calculated the two position. Let's say that it's 0.5. The maximum on X axis, let's say that it's 11 and 10.5, and here it's 11.01. So notice that we do have a bonus tolerance of 0.0887, but also with the bonus tolerance it's out of specification. Let's see what happens if we introduce 10.87. So notice the tolerance and the bonus tolerance. Yeah, so it's a nice tool to have. It's also available, as you can see here, for iOS and Android. Okay, now, so let's see also the example on GOM Inspect. So here we have the GOM part again. Okay, so we have a true position right here of this circle or this cylinder according to datums DE. So this plane and this plane. And we also have the theoretical dimensions right here to the center from the plane. So we have all the data we need to evaluate the true position. Okay, so let's make a pre-alignment. Okay, then let's make an alignment by geometrical elements. First, let's create datum A, then datum E, and datum D. Take all of them, fitting element, okay. Now let's create an alignment by geometrical elements, A, D, E, okay. Also, let's create a datum system from datum D and E, and this is it. let's hide it. Okay, and now let's extract the cylinder from here. Cylinder. It and close. Fitting element. Okay. And let's inspect the true position of the cylinder according to DE. It's circular, and let's check the theoretical dimensions: 145 and 35. 145 and 35. Yeah, it's okay. And it's 0.5. And it's deviated. Okay, but how is it deviated? On which axis we have a deviation, or do we have it on both axes? If you want to show that, then right click on the label, go to choose visualization, and go to checks, and then go to results directions, and now you have the deviation on the directions. So this is how you make a true position on GOM Inspect. There is also another true position on the drawing from GOM Inspect. It's on page 2. So we have this true position right here of this plane in regards to datum C from here. But please leave me a comment in the section below if from all the data from here we have all that we need in order to evaluate the true position of this plane. So leave a comment in the section below if you think we have all that we need to evaluate this true position or not, and if not, what is missing. Okay guys, so yeah, this is it. You can also find on my Patreon channel a drawing and a 3D model with a part. Let me just show you. So I created this part, a simple part with two position requirements on the drawing and everything that you need in order to play with it. So you can also play with this drawing and this part. You will find it free on my Patreon channel. This is it for today guys. I hope you enjoy my content. I hope you like what I'm doing. Leave a like if you want, and share and subscribe. Until next time, have a nice one.